Vladimir from Mobatec. Welcome to video help of the fourth exercise of Mobatec Modeler Introduction course. While being fourth exercise of the course, it is the second model developer exercise. Before watching this video, I strongly recommend you to read the text of the entire exercise so that you're able to follow this video smoothly. Let's start with the exercise. The exercise name is Modeling and Simulation of a Continuous Stir Tank Reactor. By the end of this exercise, you will know how to define global parameters, how to model discontinuities, how to define and add reactions in Mobatec Modeler, how to make variable plots, and how to add and use button objects. In the section 1.2, model description is given. We want to model a dynamic operation of continuous stir tank reactor, or CSTR. The tank has a single inlet at the top and single outlet at the side wall of the reactor, so the tank has an overflow outlet. The liquid inlet consists of the formic acid and methanol, which will take part in non-catalyzed esterification hydrolysis equilibrium reaction according to the reaction schematic given here. In the section 1.3, key assumptions are given. The tank is well stirred, ideally mixed, and operation of the tank is isothermal. This means that the system is a lump parameter system and it has constant temperature, which means that we will have no energy balance. All components are in liquid phase. The cross-section area is constant along the height of the reactor, and both esterification and hydrolysis reactions are taking place in this system. In the section 1.4, model equations are given. First, we have the reactor model equations. First equation is the mass balance equation, which is molar based. This is an ordinary differential equation where time is only independent variable. And we can see that the change of number of moles of any species over time equals to number of moles of that species in minus number of moles out plus the reaction rate term, which will be positive for the products as they are being generated and negative for the reactants as they are going to be consumed. In the previous exercise, exercise number 3, we have already explained that mass balances are formed automatically by the software. The difference here with the previous exercise is that we have the reaction rate term. This term will also be added automatically immediately after we create and add reactions to our capacity systems. The reason why we have molar-based mass balance in this exercise is because of the presence of the reaction rate term. Reaction rate R is predefined variable in Mobatec Modeler and is always in moles per second. If we check Mobatec Modeler Handbook mass balance generation slide, here we can see that if reactions are added to our capacity systems, then we have to use molar-based balances in order to automatically form mass balance with reaction rate term inside. As we are using molar-based balance, we have to define equation for the component molar flow rate variable in all connections connected to the reactor capacity system. Component molar flow rate variable is predefined variable in Mobatec Modeler, and we have to use this variable, so Fn with square brackets, in order to be able to calculate the mass balances of the capacity systems. So, to sum up, if we are using mass-based balances in our capacity systems, we need to define equation to calculate component mass flow rate variable Fm with square brackets. And if we are using molar-based balances in our capacity systems, as in this exercise, in all mass connections we need to define equations calculating component molar flow rate variable Fn with square brackets. Let's get back to model equations. Second equation is the reaction equation. Here we have the reaction rate given. Then we have buffer cross-section area, total molar holdup, volume, liquid level, species molar fraction, species molar concentration, and then we have liquid lines equations. First we have the inlet molar flow rate, F in, and the inlet component molar flow rate, the one that we need for the mass balance to be calculated, as we already discussed. Then we have the outlet connection equations, outlet molar overflow discontinuity equation, which states that flow will happen only when the liquid level of the origin capacity system L is higher than HP, which is height of the pipe and which will be parameter. And we have outlet component molar flow rate equation, which we need as well for the calculation of the mass balance. Small I in each variable symbol, as it is given in the beginning, represents each component, and all of the variables with I symbol will be vector variables. Let's continue. In the section 1.5, all parameters of the model are given. We can see the symbol, what is the parameter, in which model object parameter is located, and the units of the parameter. And in the section 1.6, we can see the same thing for the variables. Then we come to the section 1.7 called Things to Do. Task number 1. Use buffer tank model as a starting point. So open the buffer tank model from the previous exercise and change its name to CSTR and save it at the appropriate location. So this is our buffer tank model. We will now go Save As and save it as CSTR at the desktop. You can choose location that you like. Now our model is called CSTR. We can see that in the top left corner here. Task number 2. CSTR model physical topology. As you may have already noticed, the physical topology of the buffer tank model and the CSTR model is quite the same. We have source battery limit, one capacity system, and sink battery limit, and two connections in between. So this is the same for the both models. First, let's change the icon of the buffer tank with the CSTR icon. Go to General and go to Icons subdirectory. Here in the plant icons box you can see the available icons of the buffer tank model. Now we will go to exercise icon folder in the available icons box and find and select the CSTR icon. Then select the buffer tank icon and press exchange plant icon. As we can see, now the icon is changed. We will now increase the size of the icon a bit, like this. Now let's relocate the connection points. Right click, set graphical connection offsets, right click to exit. Let's move the outlet connection here and do the same. Right click, set graphical connection offsets, like this. Let's relocate to this place. Like this. Okay. Now our physical topology resembles the CSTR model lineup. As our starting model, the buffer tank, used mass-based balances, now we have to switch to molar-based balance. We have to switch this in each system of the model. So select the source battery limit, go to Equations tab and click Equation Sorting and Referencing button. The Equation Sorting and Referencing tab will open, and here at the very bottom of the tab you can see the equation class and it says System Mass-Based Balances. Just press, you'll see that there is a drop down menu and select mole based balances. Press done. Let's do the same for the CSTR capacity system. Again, equations tab, equation sorting referencing button, and here we change it to mole based balances. Done. And here as well we go and do the same, change it to mole based balances. Done. Task number 3, adding species to your model. We have already explained how to do this, so go to Plant Species and Reactions tab, here in General, or you can press the button in the toolbar here to access the very same tab. In the Plant Species box, we can see that water is already available as the water was added to the buffer tank model. Now let's add the other 3 species to our model database. To do that, press Define Plant Species button, change to Default Database to access all the available species, and let's first add methanol, so CH4. You can see that the filter is not case sensitive by default, but you can check this box and then it will be. So select methanol and add. Then let's add methyl formate C2H4 O2 methyl formate. So you can use both formulas or names, whatever you find more easy. And let's add formic acid CH2O2. Okay, add. Okay, now we can see that all the species that we need are available in our model database. In the source, we should have methanol and formic acid, as they will react in the reactor and produce water and methyl formate in the equilibrium reaction. So we should insert methanol and formic acid into the source battery limit system. To do that, select the source battery limit, go to species topology, and here we can see that the water is inserted to the system. This was because of the buffer tank model. So press set injected species, take out the water as water is not present in the inlet in our model, and add formic acid and methanol. Press OK. Now we can see the 3 stars in front of both species, meaning that these species are inserted to the source battery limit system. Now if we check, we can see that methanol and formic acid propagated through the connected systems and connections. Note that you don't have to inject water and methyl formate to the CSTR capacity system, as these species will be injected automatically once we create and add reactions to the CSTR capacity system. We will see this once we add the reactions later on. Task number 4, writing and adding equation of CSTR model. Here we have all the model equations written in Mobatec modular form, which, as you can see, it is almost identical to the paper written form of the equations. The only new thing that we have here is the Boolean expression form for the outlet molar overflow discontinuity equation, which is logical statement and has if, then, else, and end statements, which are all well known. If we go to Mobatec Modular Handbook, Chapter 8, Syntax, Species, Referencing, Special and String Functions, and Search Function, and we go to Boolean Conditional Expressions slide, here you can see all the possible statements that can be used in Boolean expressions in Mobatec Modeler. And to learn more on how to model different types of discontinuities in Mobatec Modeler, go to Chapter 9, called Modeling Systems with Discontinuities, and here you can learn how to model symmetric and reverse, and asymmetric and reverse discontinuities. Let's go back to our model and let's implement the inlet connection equations to our model. If we select our inlet connection and go to Equations tab, we can see that we have two equations already from the previous model, and we can observe that these equations are both very similar to the equations that we have to implement. Of course, we could delete these equations and create the brand new ones, but because the equations are so similar, it is easier to just edit these equations. To do that, go to the Main Editor tab by pressing this icon in the toolbar, or press D on your keyboard. In the Equations tab, we can see all the model equations. If you would have a larger model, and you will want to check only the mass connection equations, then you can use the equation filter and select mass connection equations, and then only mass connection equations will be displayed in the Equations tab. We want to modify the first two equations, so select the equation and then click Edit Equation. The Edit Equation tab, which is the same as the Define New Equation tab, will open. Here you can just edit and change your variable symbols in the function, and also you can change the name and just press OK. As you can see, the equation is now changed. Let's now do the same for the second equation. Also select the equation, edit equation, and just go Fn inlet molar flow rate. OK, and close. And you can immediately see that updated equations appear in the inlet mass connection. We will sort the equations later, although you could do it right away if you want, but let's first add all equations to all model parts, and then we will sort all the equations at once. Select the CSTR capacity system, go to Equations tab, and here you can see our molar-based mass balance, which is automatically formed, still without reaction rate term, because we haven't created and added reactions to the CSTR capacity system yet. Checking the equations, we can see that we are using the same equation for the cross-section area, and that other two equations are different, so we are going to delay them. Go to Define Equations, select Equation, and press Remove. Select the second equation that we don't need and press Remove as well. Press Done. As you can see, cross-section area equation is the only equation besides the mass balance equation that is now present in the CSTR capacity system. The other two equations are now removed from the CSTR model object, but they are still available in our model equation database. If we go to Main Editor tab, and if we select all equations or system equations, we can still see these two equations. If you want to reuse these equations in some other model object, then leave them and you'll be able to reuse them in all system model objects, as these equations belong to system equation class. In our case, we do not want to reuse these equations, so we want to delete them. To do that, just press Remove Unused Variables and Equations, and as these equations are not attached to any model object, they will be automatically deleted, as you can see. If you decide to first create all your model equations from the Main Editor tab, which is also an option, and then add those equations to your model objects, be careful not to press Remove Unused Variables and Equations button before you add all your equations to your model objects, as if you do that, those equations will be lost as they were not part of any model object. So, to show this option, we will now create all the equations needed for the CSTR capacity system from the Main Editor tab, and then add them to the CSTR capacity system. To create new equation, press New Equation button. Let's create the equation for the total molar holdup. Enter the function. Enter the equation name. Here you have to select which equation class this equation will belong to. Select System. Although you can select multiple classes and then you could use this equation in multiple model objects. Press OK. Now we can see that total molar holdup equation is available. Do the same for all the other CSTR system equations. Now that you have created all the equations needed for the reactor model, let's create the discontinuity outlet molar overflow equation. Press New Equation button. Here for the Boolean expressions, if you type if, you will immediately get the entire expression. I will just paste the equation, type the name of the equation, select mass connection. We see that we have no errors. For example, if we would not have AND, then we would have this at signifying the error at this point. So check always the result log to see if you have any errors. If you do have errors, then OK button will not be available to be pressed. Press OK. Now, if you select all equations or mass connections equations only, you will see that discontinuity equation is present. Now let's modify component mass flow rate equation, which is attached to the outlet connection from the previous model, to the component molar flow rate equation. Select the equation, press Edit Equation button. Here change to Fn. Change this part of the equation according to the equation from the exercise. Here change to molar. Mass connection is OK, and press OK. You can see that Fn with square brackets is recognized immediately as this is predefined variable in Mobatec modeler. Press OK. And here we can immediately see that we have successfully modified this equation. If we select all equations in the equation filter, we will be able to see all the equations needed for our model. Equations that we have modified are already added to their model objects. The ones that we have created, we will add now. Press Close, select CSTR capacity system, and press Define Equations button. Here we can see all created equations that have system equation class. That's why they're available here to be added to the system. Select one by one and add all these equations to our CSTR capacity system. Like this. Now, while having opened the Define Equations tab, you don't have to close it. You can just select the outlet connection, and Define Equations tab will immediately switch to the outlet mass connection. Here we can see the equation, which is already added to the outlet mass connection, the equation that we modified. And here we can see all the equations that have mass connection equation class, which are available to be added to any mass connection. Select the discontinuity overflow equation and press Add button to add this equation to the outlet mass connection. Now press Done, as we have added all the equations to all model objects. We can go to Inlet Mass Connection, CSTR Capacity System, and Outlet Mass Connection. The equation sorting will be done later, but before that, let's specify all variables dimensions. Task number 5, declaring variable dimensions. In the table 3, all the model variables are given by their name or symbol, description, engineering unit, unit category, and their bounds. At this point, variables K1, K2, EA1, and EA2, as well as R, are not available as they will be defined in the reaction equations. So we will declare their dimensions later on. Let's go back to the model, go to Main Editor tab, and choose Variables subtab. Here you can see all the model defined variables plus Mobatec modeler predefined variables as we explained in the last exercise. If you look closer, you can see Fm inlet mass flow user variable, which is not predefined variable and does not belong to any equation in the model. This variable was a part of the equation of the inlet mass connection that we modified. As in the previous model, we declared its dimensions, it still appears in the variables box. To remove unused variables from the defined variables, just press Remove Unused Variables and Equations. As you can see, Fm variable is now gone. Use table 3 from the exercise to declare all model variables dimensions and bounds. Now that we have defined all variables dimensions and bounds, let's continue. Task number 6. Defining and adding reactions. Let's go back to the model. So we go further with introducing ourselves with the Main Editor tab. We already learned about the functionality of the Equations and Variables tab, and today we will learn about Species and Reactions tab. Let's first check the Species tab. Here you can see all the defined species in your model. If you select one of the species, you can see the name, code name, formula, and the ID of the species in the species database. Here you can see if the selected species is taking part in any of the defined reactions, which we will be able to see once we define our reactions. Below we have parameters of selected species, and here you can add a certain parameter values of the selected species. You can add heat capacity, viscosity, etc. And then you can use that value in the equations in the model. In the equations, you will have to use a special prefix before the name of the species parameter, but we will learn about that in the next exercise. Now let's move to the Reactions tab. Use this tab to create reactions in Mobatec Modeler. At the very top of the tab, you can also select the database. You can see that our model database is currently selected and that we have no defined reactions. Even if you change to default database, you will see that you still have no default reactions, but you will have all the default species so that you can make any reaction that you want. If for some reason you want to create reactions with the species which are not currently present in your model database, we have all the species that we need for the reactions in our model database, so we will switch back to our model database and we can see here available species which we can use to make reactions. In our model we have equilibrium esterification hydrolysis reaction, but our kinetic equations are given in a form of two direct reactions. First one, the direct esterification reaction, and second one, the reverse hydrolysis reaction. So we will define two separate reactions. Let's first define the esterification reaction. Click New Reaction button, and now select methanol. Here you can set the stoichiometric coefficient value. So because it is reactant is minus 1 is good, press Add. You will see here immediately methanol. And methanol is reacting with formic acid, so formic acid as well, -1, add. So now we can see here methanol plus formic acid gives. We can click methyl formate. Now we'll go to 1, add. We can see methyl formate appearing here, and water 1 as well, add. Then press OK. And here we have the first reaction defined. Now let's create the hydrolysis reaction. Press New Reaction button, select methyl formate, change the stoichiometric coefficient to -1, as now this is the reactant. Press Add Reactant. Select water. -1 is also good. Press Add Reactant. In the notation, we can see methyl formate plus water gives, so one-way reaction. In the case that you do have equilibrium kinetics given, check this box, two-way reaction, and in the notation, the equilibrium sign will appear. In our case, we have kinetics given in a form of two direct reactions, so we will keep it one way. Select formic acid, change to 1, add product, and methanol also 1, add product, and press OK. Now we have created both reactions. Let's inject them to the CSTR capacity system. Close the main editor tab, select the CSTR capacity system, open the property browser, go to Reactions and select Define Reactions tab. Here in the Injected Reactions box you can see that it is empty, so go to Set Injected Reactions. Here in the Available Plant Reactions we have available the reactions that we have created. Select the first reaction and press Add button. Do the same for the second reaction as well, and press OK. Now we have injected both reactions to the CSTR capacity system. Our next step is to add kinetic equations to each reaction. Let's go back to exercise. Task number 7, defining global parameters. Task number 8, creating and adding reaction equations. In our reaction equations, we will make use of global parameters. Global parameters are parameters that are used globally, which means on the entire model level. They are used to reduce the equation sorting effort, especially when having larger models, and as well to eliminate the low-level modeling errors, like entering the wrong value. Those parameters are usually some known constants like gravity or gas constant or even the ambient temperature. To make use of global parameter function, you have to type glob dot prefix before the symbol of that parameter. Once you add the equation containing global parameter to a system, Mobatec modeler will automatically sort that parameter as known, and will move that parameter to the global parameter tab. There you will enter the parameter value only once, instead of sorting it and entering its value to each model object where the parameter is used. The same applies if you want to change the global parameter value. Now let's create the reaction equations. Let's go back to the model. Reaction equations are created like all other equations in Mobatec Modeler. To create them, go to Reactions and go to Equations. Here we have two reactions. The first one is selected and we see that there are no equations for that reaction. If we select the second reaction, we can also see that there are no equations for the second reaction as well. Select the first reaction, go to Define Equations. In the database you can see that there is no equation, as we still haven't defined any equation with reaction equation class. Press Define New Equation, enter the equation name, add the reaction equation by typing R equals, and then type the rest of the equation for the esterification reaction, like this. As you can see, R is predefined variable in Mobatec Modeler and is immediately recognized as reaction rate with moles per second dimension. Reaction equation class is selected automatically as we are adding equation from the system reaction equations. Press OK. The equation is already selected, so just press Add button to add the equation to the first reaction. Press Done, and we can see, if we select the first reaction, which is already selected, that we have added this equation to the first reaction. If we select the second reaction, we will see that we still haven't added any equation to the second reaction. Let's go back to the first reaction equation to explain the sys dot prefix used in this equation. Sys dot prefix is used in reaction equations to call the variables from the system where the reaction is added. So in this equation we are calling the system temperature and volume, as well as molar fractions of species 1 and species 2. These are explicitly written vector variables, which now become scalar variables, and the numbers 1 and 2 are reference to a specific species. Let's first add the reaction equation for the second reaction, and then we will set the reference numbers for both reactions. Select the second reaction, press Define Equations button, and press Define New Equation. Enter the equation name, enter the reaction equation from the exercise. We can see that reaction equation class is automatically selected as well, and press OK. Here we can see the second equation. Both equations have reaction rate variable R inside, which is perfectly fine, as each of them will be added to a separate reaction. Last created equation is always pre-selected, so just click Add button to add the second equation to the second reaction. Add, and here we have the reaction. Press Done. And now, when selecting the second reaction, we can see the equation belonging to this reaction. In this equation, as you can see, we are using reference numbers 3 and 4, while in the first reaction, we use reference number 1 and 2. Now, let's set reference species for the referent numbers 1 and 2 used in the esterification reaction equation. Select the esterification reaction, which is the first reaction, and press Equation Sorting and Referencing button. In the lower right part of the tab, we can see reference species numbers, which are still not set, and available species. As in the first esterification reaction, we have methanol and formic acid reacting. Then we will set methanol to be species number 1, so select 1 and select methanol and press Set Reference Species, and select formic acid and number 2 and press Set Reference Species. Now the software will know to use the molar fractions of methanol and formic acid in the reaction rate of the first esterification reaction. Now let's do the same for the second reaction. Press Done, select second reaction, and press Equation Sorting and Referencing button. In hydrolysis reaction, methyl formate and water are reactants, so we will set for number 3 methyl formate and for number 4 water. You can just do double click on water and it will be set as well. Press Done. Now we have only improper defined equations and uninitialized global parameters errors report. Now species referencing is done, and to summarize, all vector variables are always used in relation to species. For example, species molar fraction like here, mass fraction, concentration, partial pressure, and if you want to make them scalar, you just have to put the number inside of the brackets and later reference that number to a certain species. Before we continue further, let's declare the dimensions of the reaction rate equation parameters. Go to Main Editor tab and open the Variables subtab. Here we have to declare the dimensions and the units for the activation energy of the first and second reaction, pre-exponential factors, gas constant, and the temperature. Use table 3 from the exercise to do that. Now we have declared all variable dimensions. Let's continue. Task number 9, sorting the equations. Let's go back to Model, close Main Editor tab, and let's start from the beginning. Select Inlet Mass Connection and go to Equations. Here we can see the exclamation mark and improper defined equation message. Select the equation sorting and referencing button, and here we can see the selectable variables. In the inlet mass connection, the parameters are inlet molar flow user, so let's select it, and the species molar fraction, so the composition of the inlet mass connection. And now we can see that our equation sorting and referencing is okay, and variables fin and component molar flow can be calculated. Let's immediately enter the parameter values. You can do it either here, directly, where you can see parameters and variable values immediately, or you can go and do it here in this tab. Use the table 4 in the exercise to fill in the parameter values. Now let's sort the CSTR capacity system and the outlet connection, and then we will initialize everything at once. Select CSTR capacity system, go to equations, and go to equation sorting and referencing tab. Here we can see the selectable variables. What we know are parameters in the CSTR capacity system is the molar density, which is vector variable, so we will have to enter densities for each species, diameter, which was already selected, and the temperature. Now you maybe are asking yourself how come the temperature is present as selectable variable when we did not use temperature in any of the equations of the CSTR system. We used the temperature variable in the reaction equations which we added to the CSTR system. There, in the reaction equations, we used sys dot prefix before the temperature variable, and by using that prefix we called that variable from the system where the reaction equations are added, and that is the CSTR capacity system. And that is why the temperature variable appears here as the selectable variable. We can either calculate it, but for that we would need an energy balance, but because this system is isothermal system, we'll just select the temperature to become constant, as the system will have the constant temperature. And now we have the equation sorting and referencing okay. Now we can set the constant values, go to the constant parameter and variables values tab, and set the parameter values using the table 4 from the exercise. Here be careful to set the correct dimension, so don't use kelvins but Celsius, and don't use mole per cubic meter but kilomole per cubic meter if you are just retyping the values from the table 4 from the exercise. Now let's sort the reaction equations of the CSTR system. Press Done, go to Reaction Equations tab, select the first esterification reaction, and press Equation Sorting and Referencing button. Here, activation energy and reaction rate constant are parameters. And we can see that equation sorting and referencing is okay. In the computed unknown box, we can see that we have reaction rate variable, which is predefined and it is going to be calculated from the equation. We have gas constant global parameter, which we defined as global by typing glob dot before the parameter symbol. We will enter the value for this parameter later on. We have the temperature, which is the system parameter, as we define it as parameter in the CSTR system. Volume is also system variable, which we are calculating in the system, as well as the species molar fraction. Now let's enter the parameter values. Use table 4 from the exercise to enter the correct values. Now let's do the same for the second reaction equation. Press Done, select the second reaction, press Equation Sorting and Referencing, select activation energy and reaction rate constant as parameters. We can see that equation sorting and referencing is now okay. Go to Constant and Parameter and Variable Values tab and enter the correct values from the exercise, table 4. Now we are finished with sorting the equations of the CSTR capacity system and the reaction equation of that system. So let's move on to the outlet mass connection. Press Done, select the outlet mass connection, go to Equations tab and press Equation Sorting and Referencing button. The parameters here are beta, which is already selected as parameter, and pipe height. Now we can see that equation sorting and referencing is okay. Now let's enter the parameter values. Beta will be 100 and the pipe height will be 3 meters. Okay, we are good to go now, and now we will be able to initialize all model objects. First, we will initialize the CSTR capacity system, and then we will initialize the mass connections. Always first initialize all the systems of your model, and then after initializing the system, the connection initialization is a trivial thing. Let's continue. Task number 10. Initial conditions. Here, the initial conditions of our reactor are given. The liquid level in the reactor is 2 meters. We have 67 molar percent of methanol and 33 molar percent of formic acid. In the very beginning, we have 0% of methyl formate and water. Let's go back to model and initialize it. Before we start initializing our model objects, we have to enter the value of one more parameter, and that is the global parameter for the gas constant. To do that, go to General and go to Global Parameters, Variables and Equations. In the global parameters, you will see you have the red X, so select that tab. Enter the gas constant parameter value, which is already limited by the minimum and maximum bound, which we defined once we declared gas constant variable dimensions in the main editor tab. Enter 8.314. And now you can see that the global parameters are checkmarked green. Now let's initialize our CSTR capacity system. Select the capacity system and go to Initial Values tab. For the initial conditions, we have the liquid level and the molar fractions. Liquid level is already set as initial, so do the same for the molar fractions. Liquid level value is 2 meters. And the molar fractions are 33% formic acid, 0% water, 0% methyl formate, and 67% methanol. This system is now well posed in dynamics sense, and we are able to calculate the initial values of all system variables. You can always check whether your system is well posed in dynamic sense, or in other words, if you have specified enough initial conditions. To do that, click on the Show Init Sorting button here, and you will get the Initial Value Calculation Sorting Order tab. Below, you have 3 boxes, Selectable, Constants, and Computed Unknowns. Make sure that your selectable box is empty. If your selectable box is empty, then your system is well posed in dynamic sense. If that is not the case, and you have variables present in the selectable box, then you're not able to calculate the initial values of your system. For example, if we go back to the Initial Values tab and we deselect molar fractions as initial values and go back to Show Init Sorting, we will see that in the selectable box we have species molar fraction variable, which means that we should select this variable to get the well-posed system in dynamic sense. So, like this. To learn more on initial conditions check, go to Mobatec Modeler Handbook, chapter number 6, Degrees of Freedom and Initial Conditions, and go to Initial Condition Check slides from 1 to 5. Going back to the model, press Calculate Initial Values. Now we have calculated the initial values of all variables of the CSTR capacity system. Now if we go to the reactions initial values, we will see that they are calculated as well, as the reactions are part of the CSTR capacity system and as we have defined the parameter values of the reaction equations. Now let's initialize the inlet mass connection, select the connection, go to Initial Values tab and just press Calculate Initial Values. Do the same for the outlet mass connection, go to Initial Values tab and press Calculate Initial Values. We can see that the flows are 0, and that is because we have set that the flow will occur only if the liquid level in the tank is higher than the height of the pipe. Height of the pipe is set to be 3 meters, and we know that the liquid level in the tank, initial liquid level, is 2 meters. That's why the initial flow from the outlet connection is still 0. Let's continue. Task number 11. Display variable values. Now we already learned how to display parameters and variable values, so make the displays to resemble the picture in figure 6. To remind you, when you want to display any variable which is related to species, in this case that is molar flow, let's go back to the model. In the simulation variable box in the display property browser, we have to type the name of the variable, then lower dash, and then what is in the brackets. In this case, that is fn, lower dash, ch2o2, and so on. Now make all the needed displays. Now the displays are set. Let's just briefly check their definition so that you could check if you define them correctly. Make sure to use the correct units for each variable. And that's it. Let's continue. Task number 12, running a dynamic simulation. Let's go back to model, go to Basic Commands tab, and click on Compile and go to Simulation button. Now our model is compiled. Default simulation settings are step size of 1 second, which is fixed, and dynamic simulation type is selected. We will leave the simulation settings as they are now and run the simulation like that. Before we start running the simulation, select the reactor system, press 1 on your keyboard to get one variable table. Just close this for a second. And here type xn and press enter. Also lock the selection filter. Now we will be able to follow the change of the molar fraction of the species while the reaction is happening. Now let's start the simulation. Press Start Calculations button, the toolbar, or go to General Simulation Options tab and press Start Calculations button there. I will do it from the toolbar, and we can immediately observe the change of the molar fractions inside of the tank. You can also observe that the level in the tank is rising. Once the level becomes equal or higher than 3 meters, we will have the outlet flow. Now we can stop the simulation. It will take some time until we get the model into steady state. To do that faster, open the property browser, select the adaptive step size, and then start calculation. Let's move this here first so that we can see the values and start the calculations. Now we can see the largest step is used, and we will wait until the values are not changing anymore. And now we are in steady state. Stop the simulation. Judging from the simulation results, we can see that the esterification forward reaction is favored, as we have twice as much of the products, so water and metal formate, than the original reactants, which were metal formate and formic acid. The other way to get to steady state results is to use the steady state simulation. If we rewind our simulation by pressing Rewind Simulation button in the Basic Commands tab, you have the very same button here as well. So press this button And you'll see that initial simulation values have been restored. Press OK, and you will see that values indeed have been restored. Now select the steady state simulation type, choose Adaptive Step Size Integration Method, and press Perform a Simulation Run. What the software will do now, it will run the simulation in background until the model reaches the steady state, and it will show you the progress of simulation in the left bottom corner here. Now press Perform a Simulation Run button. You have the very same button here. So press that button, and as you can see, model converged into steady state very fast. We didn't even get to see the progress status here. That is because this is really small model and Mobatec Modeler Solver is quite fast. Mobatec Modeler is able to solve really big dynamic models, entire plant models, which can result in well over 100,000 equations that you need to solve each second in real time. And you can do that with Mobatec Modeler. As you can see here, these are the very same results that we obtained by entering the steady state while doing the dynamic simulation. The only difference is that now the simulation time here shows the exact time after which model converged into steady state. Looking at the variables table, I just realized that our capacity system is still called a buffer tank, and that is because I forgot to change its name. So to change the name of the system, go back to modeling environment, select the system, press F2 on your keyboard, and change it to CSTR. Press rename. Now we have to recompile the model again, as the variables changed their full name. So let's recompile now. Yes. All good. We select the CSTR model and press 1 to get the variable table. We will have to unlock this table because it was locked to the buffer tank system, and press again, and now lock. We can see now that CSTR is standing in the end of the variable's names. You didn't have to do this, of course, as this is just the name, but if you wanted to, this is how you would do it. Let's continue. Task number 13, plotting the variables. Let's go back to the model. We want to plot the concentration of all species in the first hour of operation of our CSTR. In order to plot variables over time, go to General and choose Plotting subdirectory. Plotting Properties tab will open. Here you have three subtabs: Plot Variables, Plot Properties, and Extras. First, we will focus on Plot Variables subtab. In order to plot variable, you have to type the exact variable name in the plot variable box here. To make this step easier, you can select variable and go right click and select copy selected variable name. Then click here, right click, paste, and you have the variable name. Then press Add Plot Variable button, and your variable will be in the Define Plot Variables box. In this case, we want to plot molar concentrations of our species, so we will remove this variable from the plot. Select the variable and press Remove Variables. Here, type C to get the concentration variables. And now we can see all the concentration variables. Here we will change the units to kilomole per cubic meter, like this. Setting the desired variable units is important, as these units will be used in the plots. Now, easy and fast way to add the variables to the plot is to select the variables in the table, do a right click, and then press Add Selected Variables to Current Plot, like this. Now, if you select one of the variables, here you can change some plotting specification of that variable. You can change the style. We will use solid. You can change the line weight. Let's change to 3 to get a bit thicker line. And you can change the color. And after doing the changes, press change plot variable. Let's do the same for the rest of the variables. So let's just increase the thickness of the line, 3. And let's change the methanol color to green, like this. Now go to Plot Properties tab. You can see that the auto scale epsilon axis is checked by default. And you can observe that the lower and upper bounds are actually the minimum and maximum value of our variables. To get a bit wider plot, you can uncheck this and set a bit higher upper bound, like this. Here we have some plotting options, which you can use to set your plots the way you want. If you don't select any of these options, then the time axis while running the simulation will appear in cumulative form, which means that you'll be able to see all the changes from the time 0 until the last time point of the integration. So let's see how that looks. Go to General Simulation Options and set Dynamic Simulation and choose Fixed Step Size. Let's go back to plotting and now press Show Update Plot window like this. Use your mouse to stretch the plotting window like this. Maybe move it a bit down so that we can see the values in the table as well. And now press Start Calculations button. As you can see, we have the methanol here. This is the formic acid and our products are here. Let's stop the simulation for a moment. As you can see, the time axis is now given in cumulative form. If you select plot only run period on time axis, then only the run period, which is set here, will be plotted. If you select show as profile plot of current values, then only the current values will be plotted, which will be dots in that case. We need to plot concentration variables of our species in the first hour of our reactor operation. For that purpose, we will choose Plot Fixed Time Axis. In the end time, we will set 3600 seconds, which is 1 hour. Now, press Show Update Plot window. Now, in this 1 hour fixed time plot, we can see the results of the first 179 seconds. Press Start Calculations again to see what happens till full hour is complete. And now we can observe what is happening. We can stop the simulation. To get faster calculations, go to General Simulation Options and choose Adaptive Step Size. Start the calculations again and watch the graph. Now we can stop the simulation. We have stopped the simulation well over 3600 seconds, and that's why you can see the lines even after the time limit here. So this is the plot that we wanted. For example, if you want to zoom in some of the areas of the plot, you can use your left mouse click, press make the rectangle and just release the click, and you will zoom in that area. To go back, just do the right mouse click, like this. You can also change the name of the plot. Go back to Plotting tab, and here change it to Concentration of Species. Let's put it like this, in kilomoles per cubic meter. And just press Show Update Plot window, and you can see it immediately. To save this plot configuration, go and press Store Plot Configuration. You can give it the name you want and choose the location and press Save. Later on, if you use this model and you want to load this plot configuration, go to Load Plot Configuration and open the configuration that we just saved. If you go to Extra tab, here you can get the timetable of your simulation by pressing Show Timetable button. As you can see, you can also easily export the timetable to CSV format. And you can have as much as 25 different plots, which you can change here, or go backwards, which will be stored in one plot configuration. As you can see, plots are having their own windows. But in Mobatec Modeler, you can also make use of embedded plot windows. To make use of embedded plot window, go back to Modeling Environment, go to Insert Objects, and choose Embedded Plots. Now you can add the plot where you want by clicking, right-click, and then you can just use your mouse to increase the plot size. Here we can see that embedded plot is linked to the plot number 1 by default, which was the plot that we made while being in simulation environment. That's why we have the very same plot here. Now if we go to simulation environment, we will see that the embedded plot is also available there, of course, and the only difference is that the plot is embedded and does not have its own window. Everything else is exactly the same as for the normal plotting windows that we showed so far. Let's continue. Task number 14, adding a button model element and making alarm indicator. Let's go back to the model and go to modeling environment. Now we want to replace the display for alpha, which we can use in simulation environment to set any value of alpha from 0 to 100 with the button object, which will have only two values, and that will be open 100% alpha or closed where alpha is 0. So delete the alpha display and let's insert one button object. To do that, go to Insert Objects and find Button Objects. Click here and you'll be able to just add a button object. You can also right click to exit. You can also add a button object if you press B on your keyboard. That is a shortcut. You can add another one. Now we can use our mouse to reshape the button the way we want. It can be a big button or a smaller button. Let's make it something like this and place it next to the valve of the inlet mask connection. If you go to Property Browser, under the button you will see Properties and Conditional Formatting tab. We will use both of these tabs to define the button object. First, if we check the Properties tab, it says here default state and it says default. In default state, our alpha is open. It is 100% open, so captation default state will be open. This is what will be written on the button object. If we press apply, it will appear here. Next, we have actions when button is pressed in this state. As button is open in the default state, once we press the button, we will enter the closed state. So here we say alpha, and we put alpha in these brackets. With these brackets, we are linking the alpha variable name to the linked object, which we will link in a few seconds. So alpha equals 0. For the linked object, select fin and then press OK. And we will also change the button color to green. And when the valve is open, the button color will be green. Press apply. And immediately you can observe that here, as this is the default state. To define the closing button action, go to Conditional Formatting tab. Here we can see the default format that we already made a few seconds ago. And to make new format for the button, press New. Here we will change to closed. And the captation which will be written on the button in this state will be closed. Here it says actions when button is pressed in this state, and that is alpha equals to 1. As the valve was closed, when pressing the button, we will open the valve. That's why alpha equals to 1. And we have the last part, and that is conditions to achieve this state, and that is alpha equals 0. We have to use the conditional statements here. And to be closed valve, alpha has to be 0. Press apply. We will also change the button color for this format, and we will select red color. Press apply again. So when the valve is closed, the button will be red and captation will be closed. As we did not make any changes to the model equations or parameter values, we can just go back to simulation environment by pressing Sim button. In order to follow the changes on the graph, we can go to plot properties and just deselect fixed time axis. And now we will have again cumulative time axis. Now let's start the simulation again and see whether our button is working properly. Go to simulation options and select fixed step size. Start the calculations. As we already explained, you can see here that the time axis is cumulative again. Now close the valve using the button. And we have some errors. Stop the simulation. It says one or more errors were encountered in the defined actions. Some actions may not be executed. Press OK, go to modeling environment, select your button object so that we can check our conditional formats. It says that the errors are found in actions, and if we go to actions, we can immediately see that instead of F, we need PH, as this is the correct name of the alpha variable. That's why it was not working. Press apply, go to closed format, and again the same in the actions, replace F with PH, and press apply. Just go back to simulation environment again, start the calculations, and now let's see if the button is working. Let's close the valve, and as you can see we have closed the valve successfully using the button. And you can immediately follow the changes on the graph due to this change. We can now open the valve, and as you can see the valve is now opened, and again we can register these changes on the graph. If we want time to go a bit faster, we can stop the calculations, set the step size to 10 seconds, and again start the calculations. You can stop the simulation now. Let's continue. Making alarm indicator, part of the same task. Go back to modeling. To define alarm indicators, we also use buttons. The only difference is that we don't define the actions in the button property tab. We will also make use of one information system and one information connection. Let's now add the information object. Go Insert New Object and choose Systems from Scratch. Select Information Type. Just click like this and you will add one information block. Right mouse click to exit. Again go to Insert New Objects and choose Connections from Scratch and choose Information Connection Type. Now connect this connection from the CSTR to your information object. Right click to exit like this. Information systems can hold algebraic equations, calculating variables which are usually not related directly to the process. Having different kinds of systems and connections is the basic idea behind the Mobatec modeler methodology, so that we can distribute all our equations over the logical model objects that they belong to. Like this, our model becomes much more easy to use and much more transparent, instead of having one big system where all the equations would be stacked together. Information connections are used to send variables and parameters values from one system to another. If we go back to the exercise, here we can see the equations that we have to add to our information system and information connection. To the information system, we are adding the equation where we are calculating the alarm variable, which can be 1 or 0, 1 meaning alarm, 0 meaning no alarm, if the liquid level is higher than the defined maximal level. And to the information connection, we have to add the equation which says that origin liquid level, which is the CSTR liquid level, equals to the target liquid level, which is the information system. So we will make use of the liquid level from the CSTR to calculate the alarm variable in the information object. Now let's add the equation to the information system. Go Equations, define new equations, and press Define new equation here. You could also define the new equation from the main editor tab and then come and add equations to the information system. Type the function, I will just paste it from the exercise. Equation name alarm, equation class system, press OK. Now add the equation to the information system. Press Done. And let's add the equation to the information connection. Go Define Equations, define new equation, and type or.l origin liquid level will be equal to target liquid level. Equation name, liquid level. Information connection is pre-selected automatically and press OK. Now add the equation to the connection. Press Done. Now let's sort the equations of the information system. As we can see, it says improper defined equations. Go Equation Sorting and select Lmax, as this is going to be a parameter that we are going to set, and set its value to 4 meters. Immediately we can calculate initial values. As we can see, there is no alarm as our level is 2 meters, so alarm value is 0. Press Done. Now we want to make an indicator for the alarm variable value, and for that we will use button object. Just press B on your keyboard and add one button object here. Right click to exit adding more button objects. Now let's define the button properties. We can first maybe reshape the button a bit, like this. Very good. Default will be no level alarm. Apply. And if we go to conditional formatting, we go new, and we will say alarm. Capitation will be also alarm, and in the conditions we say alarm variable has to be bigger than 0. Press Apply. Don't forget to link the button to the information object. Go to Properties tab. Here, select Information Object and press OK. Press Apply. As if you go to Alarm conditional format, you can see that we have used these brackets to link the alarm variable to the linked object. We will also change the color for the alarm state so that the alarm is visible. Press Apply, and that's it. Now we can adjust a bit the size of the button so that the capitation is fully visible. And we can also reduce the size of our system and also rename the system to level alarm high. Press rename. Close. Now, in order to use this alarm indicator, we have to recompile the model as we have added new systems and equations. So make node selection and compile the model. Now the model is compiled. The plot window is now empty as we have not attached the plot configuration to our model to be loaded each time when we compile the model. To do that, go to General and choose Settings, and here you will be able to see the plotting configuration that you have used previously. Just select this box and press Attach Current Simulation Settings to Focus Model. Now you can recompile the model again, and you will get the message that plot configuration, we can pin down this message, and we can see that plot configuration is now loaded together with the model. If you have used different units than the basic units, be careful to change them again, as we did use kilomoles. That's why we have 20 instead of 20,000, so change this back to kilomoles per cubic meter, like this, so that the values can be seen in the graph. Now if you start the simulation, you'll be able to see again what we already saw so far. We can stop the simulation. Let's now add one more plot to this plot configuration. Go to Plotting tab, and here change current plot to plot number 2. We can have, as we said, as many as 25 different plots. So plot number 2, change the name to liquid level. In meters. Then check auto scale and upper bound, let's say 8 meters, lower bound 0. Here everything okay. Plot variables, now we have to add the variable. It's not this one, this was from the last graph that we added. So now just open the table, clear the filter, and find here level CSTR, right click, and go add selected variable to current plot. And here it is. Close the table, and now press show update plot window. So this is the window that is not embedded. If you want embedded plot, then you'll have to go to modeling environment and add one more embedded plot and connect the embedded plot to the plot number 2. Or if you don't want to see the concentrations anymore in this embedded plot, you can just go to modeling environment, select the plot, and here change the number to 2 and press apply. Go back again to simulation environment, and you can see now that we can see the plot that we just have created for the liquid level. So let's lose this plot as we don't need it anymore, and let's start the simulation. Go to general simulation options and start calculations. Here you can see the level which is rising, and after it passes 4 meters the alarm should go on. To do that, we have to close the valve, actually to increase the resistance, so we will reduce the beta from 100 to 10. As we can see, alarm goes on once the level is higher than 4 meters. If we now go back to 100 for the flow resistance, the level is dropping and alarm is turned off once the level was lower than 4 meters. We can now stop the simulation. To save the second plot as well in your plot configuration, go to Plotting, and again go to Store Plot Configuration and choose the same plot and press Save. Yes, replace the old plot configuration. So now you have both plots, plot number 1 and plot number 2, saved in the same plot configuration. With this, we have finished the last task of the exercise, and we did some extra stuff. If you go back to exercise, in the section 1.8, you will see there are 3 questions. This time, I will let you do these questions alone and get the answers yourself. This was all for the 4th exercise of Mobatec Modeler Introduction course. Until the next help video, stay dynamic. Bye.